Hello everyone, my name is Jiapan from TU Munich. Today I will present our work, topo4d, a topographic 4D stack extension for curating and cataloging multi-source geospatial time series datasets. The main idea is simple. We work with 3D point cloud time series. Each epoch contains point cloud data, metadata, and sometimes supplementary data. But as the number of the data, sensors, and data products increases, it becomes difficult to manage and reuse these datasets. In this talk, I will show how STAC provides a metadata framework and how topo4d extends it with time-dependent metadata. As seen in the animation, with modern acquisition techniques such as UAV photogrammetry, laser scanning, and satellite observations, we can repeatedly observe the same landscape over time. This creates massive 3D and 4D datasets. The data itself is very rich, but when we want to reuse it, many questions immediately appear. These questions can mostly be answered by metadata. However, during processing or exchange of the data, the loss of metadata can make reuse and interoperability difficult, especially long-term monitoring datasets. So our motivation is to support file data management for topographic 4D point cloud datasets. Here we see the current situation. In point cloud workflows, metadata exists, but it's fragmented, folder-based, tool-specific, and often inconsistent across time. Point cloud files could include technical metadata in file headers. We may also have PDFs, TXT files, and repository descriptions. On the other hand, processing tools manage metadata differently. For example, PDA can manage metadata within processing pipelines. Py4d supports time-aware analysis by its own data structure. And Cloud Compare is widely used for interactive processing, but additional information is often stored separately. This is especially problematic for 4D point clouds, because the relationship between epochs is essential. For example, if we lose alignment information, then later users may not be able to reproduce or interpret the change analysis results. And our proposal is not to replace these tools. Instead, we introduce a common metadata layer above them. For this, we use the SpatialTemporal Asset Catalog, or STAC. STAC gives us a hierarchical structure. A catalog contains collections. A collection contains items, and each item links to one or more data assets. For 4D point clouds, this maps naturally. One item can represent one epoch. One collection can represent a time series or monitoring campaign, and one catalog can organize a multi-source 4D point clouds. STAC is designed to be extensible. Existing STAC extensions provide additional fields for specific data types, domains, or functionalities. However, for topographic 4D point clouds, we need more explicit support for metadata that changes across time and links multiple epochs together. This is where topo4d comes in. Topo4d is a proposed STAC extension for topographic 4D datasets. Its main purpose is to make time-dependent metadata a part of the catalog, rather than something stored externally. We designed a three-layer architecture for metadata curation. At the top is a metadata layer. Here, we group metadata into 5 categories: common, acquisition, processing, time-dependent, and assets. The middle layer is the topo4d STAC extension. We provide a JSON schema and toolkits to help build and validate the metadata items. The lower layer is the user layer. Here, metadata becomes STAC items, collections, or catalogs, which can be used to search, browse, and access data. To curate metadata, the first step is metadata harvesting. Our goal is to collect metadata from diverse sources and harmonize them into a unified dictionary. We organize this metadata into 5 categories. First, common data are descriptive and administrative information. Second, acquisition metadata are relevant to sensors, duration, and accuracy. Third, processing metadata indicates how users process the data. Fourth, time-dependent metadata include alignment information and temporal relationships between epochs. And last, assets metadata provide the actual data links. And the result is a structured dictionary that can be transformed into stack metadata items in next steps. The blue highlighted fields show the contribution of topo4d. Importantly, topo4d is not only adding more metadata fields, it is defining a consistent place for metadata that is often critical for 4D analysis. But these metadata are easily lost during the processing or exchange. For example, alignment transformation is essential when comparing different epochs. If this information is stored in a processing log or external files, it becomes hard to use by other people. The second step is metadata transformation. Here, the unified metadata dictionary is mapped into stack items, following the stack structure and the schema of topo4d extension. On the left, we show the item fields defined by topo4d. On the right, we see how these fields appear in a stack item as GeoJSON properties. The item includes both standard stack fields and extended fields. Two properties are especially important. Topo4d truffle meta stores co-registration metadata such as reference epoch, transformation matrix, and registration error. Topo4d product meta stores processing parameters for derived products. Together, these properties allow us to preserve the raw data description, temporal relationships, and processing details from 4D datasets. In this slide, we show an example of metadata usage. Here, it's a Isar riverbed located near Wago in Germany. This is a dynamic riverbed environment with multi-source and multi-temporal observations. The catalog integrates UAV point clouds, planet-scope satellite imagery, and derived change products. On the left, we can see the maps shows the spatial coverage of different data sources. The temporal plot shows when imagery, point clouds, and change products are available. This example catalog shows that stack catalog is not limited to only one data type. We can organize them into semantic collections in the same stack-based structure. On the right, the stack browser shows how a collection of ISA point clouds can be explored in an interactive way. Users can inspect item-level metadata, access assets, and understand the spatial and temporal context. So, the catalog becomes an entry point for searching, browsing, and reusing such a multi-source 4D datasets. The second example is an existing public permanent laser scanning dataset from Kijkdon Sandy Beach in the Netherlands. This dataset contains a high-frequency 3D time series over several months. The data are available through a Pangea repository, but the structure is mainly folder-based, with many compressed files and accompanying metadata. Our question was whether we could take such an existing public 4D dataset and make it more interoperable using topo4d stack extension. So we curated the dataset into a stack catalog, which includes thousands of items. Each item represents an epoch and can be visualized in a stack browser. This example shows that topo4d extension together with stack can also help curate published 4D point cloud datasets and improve their reusability and interoperability. To summarize, our goal is to build a full workflow for topographic 4D data management. The workflow starts with acquisition and analysis, where multi-source 3D and 4D data are collected and processed. Then comes to metadata curation, where we harvest, harmonize, and transform metadata into stack items using the topo4d stack extension schema. Then we organize curated metadata into a catalog. Each epoch or product is described as a stack item and grouped into collections. Finally, the catalog enables interactions through tools such as the browser, API, or notebooks. So as you see, we provide a full guide where you can find the resources, tutorials, helper functions, and the notebooks through the QR code. The main contribution is that topo4d stack extension makes time-dependent metadata explicit and reusable for longer data management. In this way, topographic 4D datasets become easier to find, understand, validate, and reuse across tools and communities. Thank you very much for your attention. I would also like to thank the entire team and NFDI for Earth project. The topo4d extension and related materials are available online through the QR code in the presentation. We welcome further contribution and discussion. Thanks.